Hello, my name is Aditya Shukla and I am currently doing a course under Professor Mahendra K. Verma. Okay, so my project topic is molecular dynamics. I mean, using gravitational interactions between the particles. Okay, so here is my code. Okay, so I have used the CuPy Python library to run my code on GPU to get speed up. Okay, so as you can see here, first I am importing all the necessary libraries. I have imported NumPy and CuPy, right? And for animations and stuff, I have imported the Matplotlib library. Okay, right. So first we are mounting the drive so that whatever plots or animations we are creating gets saved on the drive directly. So here is the CuPy code. All right. So first we are defining the initial parameters. I am working on a 2D simulation, right? So we have set dimension as 2, and we have set our dt and t, and the number of steps that will run depends on these variables t and dt. Okay. So first let me just mount the drive. So we have mounted the drive now, right? And we can also set the size of the box, which is 20. So the coordinates will vary from -10 to +10, and we have an initial set number of particles to 100. Okay. And yeah, initial velocities are 0, right? And initially I have set the animation as false, so this code will currently not animate anything. It will just give you the plots. So here we are initializing all the arrays in the CUDA device, right? So these variables are getting initialized on the GPU memory itself, right? So okay, yeah. So this is the main function that will that will compute the forces and update the position using the Verlet algorithm of MD, right? So as you can see, first we are initializing all the forces as 0, right? So this forces is an array of dimensions like n particles times dimension. So like suppose dimension is 2, and suppose if particles 100, so it's like a 100 cross 2 array, right? uh, Other arrays like this the current position array, the previous position array, these are all set as arrays of dimension and particles times the number of dimension, that is 2 here, right? Okay, so this is the this is the function that computes the force that is experienced by each particle, and according to the forces experienced, it is updating those positions, right? So as you can see, there are two loops here. uh, First is that a loop over n steps, meaning this loop updates time, right? And the inner loop is a loop over the number of particles, right? So we are basically first like focusing on a particular particle. We are calculating the force on this particle due to all other particles, right? And then we move to the next particle, we calculate the force on this particular particle due to all other particles, and so on, right? Right. So as you can see, first we are calculating the distance dr between the current particle and all other particles, right? So this position current array calculate it stores the positions of all the particles, and we are subtracting the position of current particle in this array, right? So we are automatically getting the dr of the current particle with respect to all other particles, right? And we are squaring this along axis is equal to 1. So this is basically like doing x square plus y square, right, for each set of distances dr, right? And also we are setting a limit because as you know, the gravitational is like inverse square kind of force. So if this dr becomes 0, or this dr square of whatever becomes 0, it will blow up, right? So this is kind of a problem with this system, because it can actually blow up. Like for example, the Lennard-Jones type of interaction, there is a kind of a cutoff distance, right? So if particles come closer than that cutoff distance, the force is actually repulsive, right? So the particles will never be at zero distance with each other. So those kind of forces will never blow up and are easy to work with. But working with gravity is kind of hard here. Okay, so anyway, next we are calculating dr power n 3 by 2. I mean, of course, I mean, if you see the expression for force, it's like x by x square plus y square, which is 3 by 2 along a x direction, plus y by y x square plus y square raised to power 3 by 2 along y direction. So with, that is what basically we are doing here. And m is the mass scale factor, right? So we can make gravity, like gravitational interaction, stronger or weaker depending on the masses of particles. The masses I have, as you can see, I have set as 500 here, which gives good interaction, right? So here next we are computing the forces, right? So this is simple. We are just summing over all multiplication dr times dr power n 3 by 2, right? So this is basically doing like x by x square plus y square raised to power 3 by 2. Same stuff we are doing along each dimension. So like uh, when this is 0, meaning we are accompanying the x component of the force. When this is 1, we are accompanying the y component of the force, right? And we are at the same time we are also calculating the potential energy of that, uh, like the potential energy of the particle, like we are simultaneously calculating that as well, right? So here the potential energy, like if we are calculating like a total potential energy, right? So so at a particular time step j, right, uh, we are doing uj is equal to uj plus sum over this minus m by this thing, which is the potential, right? So this is like doing 1 by r, right? So as you can know, expression for potential is kind of like summation I summation j 1 by rij kind of thing, right? So that is what basically we are doing here. So next, this is the Verlet algorithm, right? So this is basically the this gives you the position of particle in the next time step as a function of the position of particle at the current time step, and position of particle in the previous time step, and of course the force, right? This Wallet algorithm you can like you can study in any standard molecular dynamics book. It is a pretty easy thing to derive. Okay, and now next also, since we are kind of applying periodic boundary condition here, so there's a technicality that arises, that for example, if a particle uh, goes to the left boundary, like if it goes out of the left boundary, it will appear from the left side, right? But then this sudden change in position while calculating velocity will create a spike in the velocity, which will in turn create a spike in your kinetic energy, right? So we need to kind of deal with that, right? So that's why we are especially dealing with that, right? So these two expressions basically deal with that technicality exactly. So what is happening with, for see, this diff variable is the current minus previous, right? So if a particle were to cross the boundary, and if it is coming from this side, so difference between the current and previous will be above L, right? So L is basically as set as the box length by 2, right? So if like if box size is 20 here, so L is 10, right? So if this difference is above 10, means a particle has actually crossed the boundary and it has come from the left side. So we need to deal with this case specifically. So what we are basically doing is we are subtracting the current position of the particle by 2 times L, meaning 20, meaning by the box size, right? So for those special, like whenever this particular condition satisfies, we are uh, redoing the recalculating the next position, but this time we are decreasing the current position by a 2L, right? So we are like kind of saying that we are sending the particle back to where it was, like at wherever it crossed the boundary, and then we are calculating the next one, right? And similarly, this is for the opposite side of the boundary. When it is like on the negative side, it crosses on the negative side, right? We are then here we are adding 2 times L here, and then we are calculating our velocity, and then we are calculating our kinetic energy. So this removes those kinetic energy spikes in your system, right? Okay. Right. So okay, anyway, yeah. So here then we are applying the periodic boundary condition, right? Which is you can see here. Yeah, this is a matlab, I mean this is a pretty simple function here. So it takes an array L and the size of the box, right? And if your the if the if a particular array element is above L, then it subtracts 12, and if it is below minus L, it adds 12. So it is a pretty simple function. All right. Yeah. And then we do here the final step of the algorithm, that we assign the current position to previous position, and the next position are now current position, and this thing repeats till the next time step, right? So this is a non-vectorized version of the code, meaning it is possible to vectorize this inner loop, this loop over n particles, right? And parallel architecture, especially GPUs, benefit a lot from vectorization, right? So for example, if I run this, when visual is turned off, right? So this particular function will run, right? So if I run GPU2, like, so this GPU1 is a vectorized version of the same code, right? So as you can see, currently I'm using the n-body GPU1 function. Like, it's the same thing, but it's a vectorized version. I have vectorized this inner loop. This n particles loop is actually vectorized in this n-body GPU1 function, right? And this n-body GPU is for especially for animation, is just like the loop over n steps is missing, so per frame this function runs again and again, so that is a pretty trivial thing, yeah. And this GPU1 is n-body GPU1 is a vectorized version of the n-body GPU2, this function we were talking about, right? So I have currently this function is being run here, as you can see, right? So as you can see, with this function it took around 5 seconds. Maybe we should run it for a smaller, because yeah, anyway, right? So if we try to run the non-vectorized version, that is n-body GPU2, then it will take longer time, because that one is non-vectorized, and it will take much longer, right? So while this is running, let me explain how I am. But for for a higher number of particles, these times will vary a lot. Like for example, if we make it 1000, uh, so how I'm vectorizing it, right? So what I'm doing here, I'm adding a new axis, right? Using the cp dot new axis. There is also an np dot new axis as well. So it adds a new axis in your array, right? And the elements in this new axis is kind of the transpose of the axis just before it, right? So it's that kind of thing. By doing this, like kind of creates an n particles cross 2, which is the number of dimensions array. So like it's kind of 3D array, right? So each column of this array belongs to a particular particle, right? So like for example, the second column will store the drs of the second particles from each other particle, right? So like for example, a second column row 1 will like store a position with like the the distance between the particles 2 and 1, right? And then second column, second row will be 0, of course, because it is storing with respect to itself. Second column, third row will store between particles second and third, like that, right? So it's kind of an n particle cross n particles cross dimension kind of array, right? So that's how we are basically vectorizing, and the rest of the process is the same, right? So except for some here, now we have to take care. We during force summation we sum along axis is equal to 1, right? So as axis is equal to 1 means we are summing over the particles themselves, right? So just we just need to take care of these things, and rest of the things are almost the same, right? There is no changes here. We are also calculating the kinetic energy, because we have calculated velocity and then we calculate kinetic energy as well, total kinetic energy. Pretty simple expression, right? So here as you can see, our simulation is run. This is for the non-vectorized version. It took around 52 seconds for 1000 particles, and for vectorized version it's like around, I think, around 25 times faster, not 25, some 20 to 25 times faster. So vectorized version run much faster. Especially GPU benefits a lot from this vectorization, because there are a lot of the streaming multiprocessors there, as compared to your sequential code, right? So I have also written sequential code here. It's kind of the same thing as above, mostly the same. Is just using numpy instead of cupy, right? So this we have n body numpy 1 function. This is a vectorized version, and this n body numpy is like a non-vectorized version. So okay, so it's time to look at the results, right? So I have run the same code in a little powerful machine, because to look at the results properly, we have to run it for a longer time and a higher number of particles, right? So I'm running this code on Bernard. It's a CPU cluster here at ITK, right? It was provided by Professor Mahendra Verma. Right, okay, so this has an Intel Xenon CPU. It's an 8 core CPU, and it uses an NVIDIA 3090 GPU as well, right? So it's a much faster GPU, like that. That vectorized versus non-vectorized performance here is 40 times as compared to 25 times of Colab, right? So we have ran for a thousand particles. As you can see, this is the kinetic energy, potential energy, total energy plot. And as you can see here, the energy is not exactly conserving here. This is due to periodic boundary condition. It is kind of spoiling the energy conservation here, right? So dealing with this, one way would be to remove the periodic boundary condition entirely, and just look at the particles as they interact, right? So that could be one of the things, but as you can see, like at for a high number of particles, like for 15,000 particles, at least after some times the energy conservation is being followed, right? And this is the animation of it. So as you can see, a cluster is forming here, right? So as you can see, a cluster is being formed, and the particles which are going at the boundaries are coming back. So periodic boundary condition is properly applied, right? So yeah, and this is the speed up plot. As you increase the number of particles, the speed up increases, right? So this is the compared between the numpy and cupy code. So this speed up is between them, so it kind of saturates near 28 to 29 basically, right? If there were no boundary conditions, you kind of get this kinetic energy spikes, but speed up is very good. So near 10,000 particles, it reaches kind of 80 and 90 times speed up. But with boundary conditions, it saturates, because those if else conditions kind of spoil the speed up kind of. Okay, so that's it. Thank you.